All right, welcome ladies and gentlemen. This is video number 4 and our final video in our nuclear chemistry unit on half-life calculations. And you'll need your notes open to where it says half-life video number 4, half-life calculations. You will also need your reference table and a calculator. So in this video, I'm going to be going through how to perform the half-life calculations. But before I get started with the sample problem, a half-life problem will always give you two types of numbers, two types of data. And the two types of data are mass or amount. They'll give you mass numbers, they'll give you amount values, and they'll also give you time values. And you need to categorize them accordingly. In the mass and amount category, there'll always be two possible types of numbers: an initial mass and a final mass. Or an initial amount. It could be a fraction, it could be a percent, so we're going to call that amount, initial amount and final amount. In the time category, they're also going to give you two types of numbers: the total time and the length of one half-life. And in any given half-life problem, basically they'll give you 3 of these values and you'll need to solve for the 4th one. So one of them is going to be an unknown. And the key to answering this, because there is no formula for you to use, there's no equation that you can just plug this stuff into, is always be thinking, how many half-lives? Because that's not the, it's not the final answer, but I guarantee you this is going to be the middle step to any given half-life calculation. So we're going to look at 4 different half-life problems, literally solving for one of each, so you can kind of see the different ideas. So a radioactive element has a half-life of 4 hours. What fraction of an original sample will remain at the end of 12 hours? So just like in the previous one, we're going to split up, we're going to analyze the data, and we're going to put it into 2 categories: mass/amount and time. And we're going to figure out what they gave us and what we need to solve for. So again, with mass and amount, there's always going to be an initial amount and a final amount. And with time, there's always going to be a total time and a 1 half-life time. So what did they give us? Has a half-life of 4 hours. Okay, boom, so that's the length of 1 half-life, 4 hours. What fraction of an original sample will remain? What fraction will remain? So that's an amount, because fraction, right? Fraction means, 1/2, 1/4, 1/8, etc. So this is an amount. And they're asking for the amount that will remain, which means the final is our unknown. At the end of 12 hours, well, that's the total time, so that's going to go there, 12 hours. Now, because they are talking fractions, we do actually know the initial amount, because what's our initial fraction? Our initial fraction is always 1, right? What fraction remains? It's kind of like saying what percent remains. Well, what percent did you start with? You know you're always starting with 100%, so you know you're always starting with, if it's in terms of fractions, with an amount of 1. So how am I going to do this? It's looking for the final fraction. The intermediate question is always how many half-lives, right? We always want to be thinking that. How many half-lives? And when I look at the data, notice how I have more information here about time. That means that I'm going to figure out the number of half-lives from this stuff, and that's going to be my first step. So how can I figure out number of half-lives from total time and 1 half-life time? Well, 1 half-life is 4 hours, but I've let it sit for 12 hours. So if I divide the 12 hours by the 4 hours, I know that 3 half-lives have elapsed. You're always going to be dividing time by itself in order to find the number of half-lives. So 3 half-lives total, right? Each half-life is 4 hours. So let it sit for 12. That's a total of 3 half-lives. Well, now I can take this 3 half-lives and I can go back to my amount. And I know I've let this initial amount of 1 sit for 3 half-lives. So after 1 half-life, right, what fraction would I have? I'd have 1/2 left. But I didn't let it sit for 1 half-life. I let it sit for 3. So after 2 half-lives, again, you're taking half of the amount. Half of a half is 1/4. But I didn't let it sit for 2 half-lives. I let it sit for 3 half-lives. So I'm going to do that one more time. The 3 half-lives, again, take 1/2. And I'll have 1/8 remaining. And that right there is the answer to the problem. After 3 half-lives, again, each half-life is 4 hours. You let it sit for a total of 12 hours. You started with an initial fraction of 1. You will have 1/8 of the original sample that is still radioactive. Second problem. A sample of strontium-90 has a mass of 1 gram after 116.4 years. Calculate the mass of the original sample. So same exact thing. I'm going to divide up my information into mass, amount, info, initial and final. Initial, final. And I'm also going to divide up my time into the total time and the 1 half-life, because these are always the 4 pieces of information you need in a half-life problem. Simple strontium-90 has a mass of 1 gram after 116.4 years. So this mass right here, a mass of 1 gram after, because they say it's after 116.4 years, that means that is the final mass. And you've let it sit, that's the total time for the 116.4 years. Calculate the mass of the original sample, right? Calculate the mass, but the original sample. So that's the initial, right? Because that's the initial amount that we have. So that's our unknown. Notice how we're missing a number here, though, right? We need to know this value. There's literally no way to solve this problem unless you know the length of 1 half-life, but it doesn't say it in the problem. Oh, what are you going to do? Oh, they said strontium-90. Oh, perhaps we have a reference table that would tell us information about strontium-90. Perhaps we have something like table N that lists the lengths of half-lives for a whole bunch of different radioisotopes. So if you realize that you need a piece of information to solve the problem, which we do here, you have to look it up. So you go to table N, you look it up. Strontium-90 has a half-life of 29.1 years. So this is straight off of your reference table. So same thing before. How many half-lives? That's always our intermediate calculation. And same thing as last problem, we have more information about time, so we're going to start our calculations there. We want to figure out the number of half-lives. Each half-life is 29.1 years. We let it sit for 116.4 years. So if we divide, we can figure out that we have let it actually sit for 4 half-lives. And then we can take that number and go back to mass. Now this problem is a little bit different. It's asking for the initial amount, right? Some starting value. But we also know that we let the starting value sit for 1, 2, 3, 4 half-lives, right? We don't know how much we started with, but we know we let it sit for the 4 half-lives. And we also know that at the end of the 4 half-lives, we have 1 gram left. Well, how are we going to do this? We're actually going to work backwards here, because each half-life you're taking half, right? So what number did we have to take half of in order to get 1? Meaning instead of taking half, now we're going to double it, we're going to go backwards. So we must have had 2 grams here, right? But we let it sit for 4 half-lives. So we're going to do this again. So what number when we took half of us gave us 2? Well, we're going to go backwards. We're going to multiply by 2 now. 4. Keep going. What number when we took half of us? Half of it gave us 4. Well, that's 8. And then what number when we took half of it gave us 8? 16 grams. And that is the answer to the problem. What is the original mass of the sample? We know we let it sit for 4 half-lives. We know we ended up with 1 gram at the end of 4 half-lives. So then you're just working backwards. You're basically multiplying by 2 4 times instead of dividing by 2 4 times. That's the idea. A sample of fossilized wood that when alive would have contained 24 grams of C14 now contains 1.5 grams of C14. Determine the approximate age of the sample. Same thing, mass / amount and time. So mass amount is always initial and final, and time is always total and 1 half-life. So we pull the numbers apart. That when alive would have contained 24 grams, now contains 1.5 grams. So would have contained 24 grams, that was the initial amount in the fossilized wood, but now After time has elapsed, it only contains 1.5 grams. And then it says determine the approximate age of the sample. Well, that's asking for the total time. It's how old is the sample? What is the total length of time that this thing has been sitting around? So we need to know the total, but again, we don't know the length of one half-life. But we do know that it is C14, which means reference table, which means table N, which means looking up C14 in table N and seeing that it has a half-life of 5,715 years, and we're going to use that information. Again, your middle step is always the number of half-lives, figuring that out somehow. Now, though, we have more information about the mass/amount. Notice we have two numbers there instead of only one number over in time, so we're going to work out the number of half-lives this way. And the way that we were going to work out number of half-lives from mass/amount is not by dividing them. You can't divide 24.1.5. You can only divide mass by 2. But what we're going to do is we're going to divide our mass by 2 until we work out the number of half-lives, meaning I'm going to take my 24 grams, which is my initial amount, I'm going to let it undergo one half-life, i.e. take half of it, and I get 12 grams. Is that the final amount that we have? No. So I'm going to keep going, meaning we must not have had one half-life. So what about 2 half-lives, meaning take another half of it? Well, I get 6 grams when I do that. Is that the final amount that we have? No, the final amount we have is 1.5 grams, so I'm going to keep going. So, okay, if it sat for 3 half-lives, then we take half of that again, we get 3 grams. Is that the amount that we had at the end? No, we had 1.5 grams, so we have to keep going. So if we let it sit for a 4th half-life and take half of it, now we have 1.5 grams. Is that the final amount that we have? Yes! Yes, it is. So what this tells us is that this must have undergone 1, 2, 3, 4 half-lives. Now that is not the answer to the problem. The problem is asking for time, total time, right here, right? But we know that we let it sit for 4 half-lives. Each half-life is 5,715 years. So if we just do 5,715 years times 4, because you let it sit for 4 half-lives, we can get the total time, and the total time, therefore, is 22,860 years. Right, this is what we're doing. The 4 came from the fact that we had to divide the 24 grams by 2 once, twice, 3 times, 4 times in order to get the 1.5 grams that the problem told us we ended with. And then last sample problem, a 64-gram sample of germanium-66 is left undisturbed for 12.5 hours. At the end of that period, only 2 grams remain. Calculate the half-life of this material. Mass amount data, initial and final, and time information, total, and 1 half-life. So what did they tell us is left undisturbed for 12.5 hours. So that is the total length of time because it does not tell us that that is the half-life time. At the end of that period, we have that number first, a 64-gram sample, so that's an initial one. Only 2 grams remain, so that's the final one. Calculate the half-life of this material, which means we don't know this number, and it is not in table N, so we have to actually figure that out. Again, always be thinking how many half-lives. That is always your, that is always your intermediate step in a half-life problem. And we're going to start our math with the mass because we have more information about it. And just like the last one, we're going to be taking the mass, the initial mass of 64 grams and dividing it by 2. You can only ever divide amount by 2 in half-life. It's literally half, right? How half of it is decaying, and until we get to the final amount that we have. So after 1 half-life, if you divide 64 by 2, you get 32 grams. That's not the final amount that we have, so we're going to do this again. After 2 half-lives, you take your 32, you divide that by 2, you get 16 grams. That isn't the final amount we have. We've got 2 grams, so we're going to keep going. 16 divided by 2 again is 8. That is not the amount that we have. We've got 2. We're going to keep going. So we let it go undergo a 4th half-life. We take half of that. We get 4 grams. That is not the amount that we have. We've got 2 grams. So we got to do this again. We let it sit for a 5th half-life. Take half of it. We get 2 grams, which is the final amount that we have, which tells us that this thing must have undergone 5 half-lives, right? Again, that's not the answer to the problem. The problem is asking how long is 1 half-life. What we do know, however, is that 12.5 hours is equal to 5 half-lives. So in 12.5 hours, it has decayed 5 times. So what can we do? Well, we can divide the 12.5 hours by 5 in order to tell us how long 1 half-life is, right? In 12.5 hours, it's undergone 5 half-lives. So 1 half-life must be 12.5 divided by 5, which means that 2.5 hours is the length of 1 half-life, which is exactly what the problem is asking for. So we're going to practice with this in class. We're going to spend plenty of time practicing with this so that you feel comfortable with this type of problem.